Hi everyone, my name is Sharli Thompson, and I want you to imagine this. You're running a 5K, your legs are moving, your heart's pumping, and you can feel your breath picking up with each stride. At first, it's kind of hard for you to catch your breath, but you start to settle into a rhythm. You're breathing fast, but it feels steady. This is the moment when your body is working hard but starts to balance out. This is a perfect example of steady state endurance and how our respiratory system adapts to meet the body's needs. So, how does steady state endurance exercise disrupt respiratory homeostasis? So, during a steady state endurance exercise, our respiratory system has to meet the ongoing energy demands of our working muscles, but at rest, our breathing keeps our oxygen, carbon dioxide, and our blood pH fairly stable. But as soon as exercise begins, this balance is intentionally disrupted. So that means like our oxygen demand rises, our CO2 production goes up, and then the body has to adjust ventilation to support the aerobic metabolism. So some key changes or variables that change, which is our oxygen demand, which is our muscles extract more oxygen from the blood, creating a steeper gradient for oxygen to move from our lungs to our blood and then to our muscles. So our breathing increases, and it just works with our heart to make sure that the delivery stays safe. Our oxygen delivery stays safe. Then our carbon dioxide, which is more oxygen. When we use more oxygen, more carbon or CO2 is produced. And if our lungs can efficiently move the CO2 there efficiently, then there's CO2 buildup that lowers our blood pH and then causes acidity. But with proper ventilation, then that can be prevented. Also, our blood pH, so it is our hydrogen ions from ATP breakdown and our carbonic acids from our CO2. It lowers the pH slightly, but your breathing automatically adjusts to removing CO2 and keeps the acid levels under control. And then lastly, which is our ventilation, which is our breathing, first increases in tidal volume, which is the amount of air per breath, then in breathing rate as intensity rises, which just keeps the oxygen and CO2 balance. So at the onset of exercise, ventilation increases quickly, and then our body anticipates what we need. So once we settle into like steady state, our oxygen delivery, CO2 removal, and an acid base all balance are matched to meet the muscle's demands. So this is important to know. This is not like a return to rest, but a new higher level steady state that allows you to sustain exercise. So then we have our feedback and control mechanisms. So our breathing is controlled by a combination of feed forward and then feedback mechanisms. So our feed forward is at the start of the exercise when your brain anticipates the demand and increases ventilation before CO2 or oxygen levels change. Then there's the feedback, which is as exercise continues, there's sensors that detect chemical and mechanism changes and send signals to the brain, and it adjusts your breathing in real time. We have like 5 sensors that help with our breathing and everything. So some of them, well, I'll just tell you what they do. So they detect CO2 and pH change. Even small shifts make you breathe more. It monitors oxygen, CO2, pH, and oxygen. Especially at high intensities and altitudes. Another one senses movement and stretch, and it helps increase ventilation at the start. There's a muscle one which detects hydrogen ions, lactate, and potassium, which triggers more breathing as intensity increases. And then the pulmonary stretch receptor, it monitors lung inflation and it helps regulate breathing depth. So then our control center, this is the medulla and pons that integrate these signals and automatically adjust breathing rates and depth. They are anticipating the exercise before chemical changes occur, preventing large swings in our blood gas and pH. Then there's our effectors, which is like our diaphragm and intercostal expands the chest for deeper breaths. At high intensities, at higher intensity, the accessory muscles help move out more air. Then there's breathing. First increases in tidal volume, then in frequency, and then lastly is after exercise, breathing slows down gradually as like our signals from our chemoreceptors decrease. So, chronic adaptations on how our body adjusts over time. So, when you perform a steady state endurance exercise regularly, your respiratory system adapts to handle stress. So, beneficial adaptations include stronger fatigue resistant diaphragm and intercostals. It improves breathing efficiency. So, same oxygen delivery and CO2 removal, but just less effort. There's higher ventilatory threshold, which means you can exercise harder without feeling out of breath. And then last, a decrease in perception of breathlessness due to better coordination between the brain and the muscles. So some adaptations which you can get if you don't train properly, which is respiratory muscle fatigue, poor breathing patterns, exercise-induced bronchial constriction, and then reduce performance. This shows why recovery is just as important as training itself. But a lot of us miss the recovery part. So some applications to exercise prescription in clinical population, which is pretty much we need to understand like the respiratory homeostasis so we can design safe and effective exercise programs. So with our older adults, as we age, our lungs aren't as elastic and our breathing muscles maybe weaker. But it doesn't mean that they can't exercise. It just means that they have to start slower. They have to take their time and gradually increase their intensity. But short bouts of like activities or just breathing exercises can help them with their endurance and safely without overexertion. So a good machine to use is like the New Step. It's really good because it's like a full body workout and they seem to love it. Also, it's also good. The New Step is also good for pulmonary patients as well because they don't feel as if they're out of breath as soon as they start to move, even though they take it at a very slow pace. Then lastly, steady state endurance exercises challenges our respiratory system by increasing our oxygen demand, CO2 production, and acid-base stress. Over time, through precise feedback mechanisms in our training adaptation, our breathing becomes more efficient and better able to maintain stability under stress. So undergoing these mechanisms allow us to design programs that are safe, effective, and tailored to our older adults and our clinical population. But I also would like to hear your thoughts on how respiratory homeostasis compared to other systems like cardiovascular systems and thermoregulars. Are some systems more limiting, and how does it affect the training or recovery strategies?